Hi guys, this is 6D, which is graphing derivative functions, which is something that you did last year, but we're going to spend a little bit more time on it. Something that's really important to recognize when we're sketching not only our normal functions, but your derivative function as well. So when I say normal function, I mean just f of x, as it says on the sheet here. So when we're sketching f of x, we're comparing y to x, aren't we? So this is your y-axis, that's your x-axis, and the coordinates are just your x compared to y. Okay, now over here when we're sketching the derivative function, we've still got x, but on your y-axis, that's actually the gradient. So what is going to happen if you see in your gradient function, if the line is above the x-axis, that means you've got a positive gradient value. That means for whatever value for x the line's on, the gradient will be positive. If the line is hitting the x-axis, that means your gradient's 0. So whatever x value the line hits the x-axis, that's where you've got a stationary point or a gradient of 0. If the line is below the x-axis, they're your negative gradient values. So whatever x values that line has down there, they have negative gradients at those x values. So we've got a few examples here for you guys to look at. These dot points here are pretty much what I said before, and we're going to practice with it. So I know there's a lot of writing there, but it's actually not too difficult. One extra thing that I've added here is, and this is more so for your normal polynomial functions. So when you've got x to the power of whatever 5, 4, 3, 2, 1. The graph of the derivative is going to be one power lower. So if you have a cubic function, if you're graphing the derivative, it's going to be a quadratic, so a parabola. And you might see how that works when you have a look at the power rule, because remember when you differentiate, the power goes down 1. So that makes sense that we would go from a cubic graph to a quadratic graph, or perhaps a quadratic graph to a cubic graph, etc., etc. Okay, so let's start having a look at these. Now, if I look at this line here, we can see that that has a constant gradient, doesn't it? Okay, so we can also see by using rise over run that the gradient is going to be -3. So when we sketch the graph over here, we need to show, or the graph of the gradient function or derivative function, we need to show that the gradient's going to be -3. So I'm going to show that this is the graph of the gradient function by doing that. And I want to show that the gradient is always -3. So -3, let's just say that's around there. And the gradient is always going to be -3. So we can see that for every x value, the gradient's -3. Alright, let's move on to B. Now this has two different sections. So this has a section before x is 0 and a section after x is 0. Both of them have constant gradients, but the gradients are different, aren't they? So we've kind of got a little barrier in the middle. We're going to have one gradient before x equals 0 and another gradient after x equals 0. Now, I don't know exactly what this gradient is here. It hasn't given me any numbers, but I do know that it's negative. So because it hasn't given me any details about that, I'm just going to say it's somewhere around here, and it doesn't include x equals 0. So we've shown this section. Now let's have a look over here. This has a constant gradient as well, but the line's flat. A flat line has a gradient of 0 because it's not sloping upward and it's not sloping down. So we're going to have a gradient of 0 going along just here. So we can see for these negative values for x, we have a negative gradient, and for these positive values for x, we have a gradient of 0. Alright, let's move down to the next one. Now, I'm going to bring up a really important point here, and it actually says it up here. It's our first dot point. Whenever you have a stationary point, so you might have a point of inflection or a turning point here, that's when the gradient's 0, isn't it? So if you're sketching a gradient function for a graph that has a turning point, what I think you should start with is where the gradient's 0. So we can see here that we have a turning point at -1 and 4. that's where the gradient is 0. So where x equals 1, the gradient is 0. Negative 1, sorry. So negative 1, I know my graph's going to run through that point. Alright, now we're kind of splitting this up. I want to have a look at what's going on before that stationary point and what's going on after that stationary point in terms of gradient. So before the stationary point, I can see that the gradient is positive. So that means my line for our gradient function, it's going to have to be above that x-axis. It's got a positive gradient value. So we can see that it's actually quite steep, and then it kind of shallows out a little bit or flattens off a bit before it gets to 0. So it starts off super steep and then eventually gets to 0 at x equals 1. Now let's have a look at what's happening afterwards. So after it, we can see that we have a negative gradient. It's sloping down. So it starts off reasonably flat and then gets steeper and steeper down as time goes on. So it starts off at 0 and then gets steeper and steeper down. And that would be it. Now let's have a look at this graph. This is a quadratic, so x to the power of 2, which means our derivative function should be x to the power of 1, which is linear. That is linear, isn't it? It's a straight line. So we're done. Finish with that one. Let's move on to the next one. Alright, so even though these two look slightly different, we do it in the same way. So that first step that I took over here was having a look at where the gradient is 0. So for this one, I can see the gradient 0 here, the gradient is 0 here, and the gradient is 0 here. So the gradient is 0 at x is negative 2, x is 0, and x is 1. I'm going to start off by showing those points in this graph over here. So negative 2, that can be there, 0, and 1. Awesome. So now what we need to do is have a look at what the gradient looks like between these stationary points. I'm going to put some little vertical lines here just to break it up for us so it's a bit easier to see. Alright, now let's have a look at before x equals minus 2 here. So before x equals minus 2, we can see we have a positive gradient. Sorry, not positive, a negative gradient before it gets to 0. So it's going to be down before it gets to 0. Now let's have a look at the next section. We can see that this section has a positive gradient. So it starts off reasonably flat, then steepens up, and then flattens off again. So that means it's going to be 0, and then get a little bit steeper, and then it's going to come back to 0. So it's going to end up looking like that. The next section we have a negative gradient, but again, starts off reasonably flat, gets steeper in the negative direction, and then flattens off again. So it has to go down here, the gradient gets back to 0 at x equals 1. In this last section, we can see that we have a positive gradient. Reasonably flat at the start and then gets steeper. So it's going to keep on going up like that. Now let's have a look at these two graphs. So the graph of the original and the graph of the gradient function. This is a quartic graph, isn't it? So if we differentiate, we should end up getting a cubic. That looks like a cubic graph, doesn't it? So we're all good. Okay, let's move on to the next couple. Now this one is a little bit harder. What I think we should actually start with on this one is the asymptote. You see how this one has a vertical asymptote at x equals 2? If there's an asymptote there, that means the line is never going to go there. So how can we have a gradient if there's no line there? So that means our asymptote is going to transfer across to our gradient function as well. And that's at x equals 2. Awesome. Now, let's have a look at stationary points. I can see that there's a stationary point here. So the gradient is 0 where x equals 1. So I know it's going to go through this bit here. Okay, so if we start here, actually I'm going to put a little dotted line here. Again, this is not an asymptote, this is just helping me break it up. We have the gradient starting reasonably flat but then it's getting steeper in the negative direction and then comes back to 0. So it starts off reasonably flat, gets steeper in the negative direction, but then it has to come back to 0. So it's going to look like that. Now, sort of coincidentally, it looks really similar to what the original function looks like anyway. Now, after this stationary point, we can see that the gradient's positive, isn't it? So the line in our gradient function is going to be up above that x-axis, and it's getting steeper and steeper and steeper. So the line's going to keep on going up, up, up like that, and keep going. And that would be it. Now that's a little bit wobbly. I think it's going to look more like that, but hopefully you get the general gist. And the line keeps on going that way as well. Okay, let's have a look at this last example here. Now this is similar to the first couple in the way that they're just straight lines, aren't they? Now we have a line that starts at x is negative 3 and finishes at x is 0. Let's work out what the gradient of that line is. So if you do your rise over run, the gradient should be 2/3, which is positive. That's a positive gradient, yeah? So it's going to be just a constant gradient. And remember, this axis is showing us what the gradient is. So the gradient is, what was it? Rise over run? Yep. So 3 on 2. No, 2 on 3. What am I doing? There we go. Now I've done like a closed circle here. It's actually open circle, isn't it? Because it doesn't include that point where x is 0. So let's make that open. But on the other side, it does include where x is negative 3. So I'm going to put that there, and I'm going to show that point as well. There we go. So we've ticked off this bit, that one's done. Let's now have a look at this section here. So that's a negative gradient, isn't it? So we showed the positive gradient up here. If it's a negative gradient, it's going to be down here, and it is constant, so it'll be a flat line. Now let's have a look and see what the gradient of this is. So rise over run, so the rise is negative 5 over a run of 3, so it's minus 5 on 3. Now that keeps on going until x is 3. And we're finished with those ones. This next example here involves using the CAS, so I'll show you using that screencast.
Alright, so onto this second example. Now it's asked us to use our CAS to find f-x for that function above, or in other words, it's asked us to differentiate using our CAS. Alright, so we haven't done this yet, but this is going to be a pretty important skill, because if you're in an exam too, what's the point of differentiating by hand if it's going to take you a longer amount of time? It's smarter to use your CAS to free up more time later for actual problem solving stuff. It is still important to be able to differentiate just by hand, because that will occur in your exam 1. But this is a great time-saving strategy. So to differentiate, we're first going to go to menu. I need to calculate first, don't I? So menu, calculus, that's our topic, and then we want to find the derivative. There we go. Okay, so what you're going to do is in this section enter the rule that you want to differentiate. So in our case it's x minus x squared all squared. Okay, now you'll see that there's another box just here. Now that's going to be filled with the letter that's in your rule. So the letter in our rule is x. If it was t minus t squared all squared, the letter that we put in here would be t. So yeah, whatever letter it says in here. And all you need to do is press enter, and there we go. We have our derivative, or f-x. Now B has asked us to plot f of x and f-x on the same axis. So let's do that. We've actually already typed both of them in. So here is your original function. Here's your derivative. I'm going to try to save some time and not even bother typing them again. So you can actually copy and paste. So Control C and Control V work on the computer, which I'm using right now, but also on your CAS as well. So I've just copied that. There we go, I've pasted that in. So that's our original function. You can't really see it that well, so I'm going to zoom in a little bit because I can see there's some minimums and maximums here. There we go, so we can see them a little bit better now. I'm going to go back to my calculator. I've already got the derivative. I'm going to copy it, move across to my graph, paste it. There we go, I've got that one as well. Now, blue is our original function, red is our derivative. Now this is a little bit strange that we've got them both in the same axis, considering the blue one compares the value of x, which is along here, to y, which is up here. But the red one, the derivative, that's still comparing x, but your y-axis is different. That represents the gradient. So we've got the y-axis representing two different things here, which is a little bit strange. I think in the past you have been asked to sketch both in the same axis. You might do it on your CAS anyway. So yeah, just be really aware that the y-axis isn't necessarily representing the same thing for both of these graphs. Now with C, it says find where f of x and f dash x are maximums over the domain from 0 to 1. You guys know how to find your maximums and minimums using your CAS. Hopefully you should have been doing it last year. Just a reminder though, menu, analyze graph, maximum or minimum, whichever one you're looking for. So if we're after a maximum, we'll choose this graph here because there's a couple, we need to choose one. I'm choosing that graph, lower bound, upper bound, and that's told us where our maximum is. Don't worry too much about C for the time being. We're going to get into some more stuff about that later on.
So we have two exam questions for this section. I'm not going to do this first one straight away. I'll do that next because I think that one is a little bit harder. This one's more straightforward. So with 95, we have f of x graphed here, so y compared to x. We want to know which one of these could be the graph of the derivative function of this one. So it's important that we identify a few key points, which is where the gradient's 0, where it's positive and where it's negative. So I can see the gradient is 0 here, it's a stationary point, and we also have another stationary point here. So we know that the gradient is 0 where x is minus 3 and where x is 0. So let's have a look over here. This one doesn't show a 0 gradient at minus 3. The line should be here. So this one doesn't work. This one has a 0 gradient at minus 3 and 0. This one has one at minus 3 and 0 as well, except there's another at minus 5. There isn't one at minus 5, so it can't be that one. This one shows a 0 gradient at minus 3 and 0, could be that one. This one has another 0 gradient at minus 5, so it can't be that one either. So we've narrowed it down to B or D. Now once we've done this, let's have a look at where the gradient is positive and negative. I'm just going to look at before this first stationary point. So we can see that before that first stationary point, we've got a positive gradient. Alright, so let's look down here. Now this is showing that the gradient's positive beforehand, so it could be this one. This is showing that the gradient's negative beforehand, so it can't be that one. Your answer's B. Alright, so let's go back up to 91. Now 91's a little bit harder because you're sort of working backwards. Instead of giving you the graph of just your normal function, they've given you the graph of the derivative function, and then they're asking which one was the original. So it is working a little bit backwards. But what we can get out of this graph here is we can see that there's going to be 0 gradient here, 0 gradient here, and 0 gradient here. So you've got 0 gradient where x is 0, and then you've got one where it's negative and one where it's positive as well. So let's have a look here. Does this one have a 0 gradient where x is 0? No, it doesn't have a stationary point there. Does this one have a stationary point where x is 0? No. Does this one? No, I can't even see any line there. This one does have a stationary point where x is 0. Also has a stationary point for a negative x value, and another stationary point for a positive x value. So it could potentially be that one. And this one has the same sort of thing. See how it has a stationary point at a negative x, stationary point at 0, and a stationary point at positive x. So it could be either of these two. Now we're going to actually have a look at what the gradient's like between these points. I'm just going to start off with this first section. So this is showing the gradient function. So this graph is telling me that before this stationary point, the gradient is negative. So before that first stationary point, the gradient's negative. There's the first stationary point. There's the first stationary point. This one has a negative gradient. Could be that one. This one has a positive gradient. It can't be that one. So the answer has to be D.